Hi, everyone. It's my pleasure to invite you to this webinar, Why are Enclaves the Savior for Cloud Security? As we just saw yesterday, there was a big consortium announcement by Linux Foundation around confidential cloud that involved participants such as Intel, ARM, Microsoft, Google, IBM, and others. To explain to you why the world is moving towards Enclave for cloud security and privacy, we are having this webinar today. My name is Ambuj Kumar. I'm co-founder and CEO of Fortanix, and I'm joined by Simon Johnson. Simon is senior principal engineer at Intel, and he was one of and is one of the original architects of this whole Intel SGX program. As you know, Intel has invested lots of energy, lots of research in crafting this software guard extension architecture. They have worked really hard, starting from defining instruction set to building servers to support those. So I'm very happy to have Simon. Simon, please start.
Hey, thanks, Ambuj, and welcome everyone to this. And I really want to appreciate Ambuj and the team at Fortanix for setting this up and giving us the opportunity to talk about SGX and the role it's going to play in cloud security. So my role here really is today is to give you a very, very light and quick introduction into the problems that we saw when we were developing SGX, and how the sorts of things that we're going to add to SGX and why that's going to be useful in securing the cloud. So let's move on with the content straight away, please. Standard disclaimer. Okay, so Intel was a silicon company and now claims that it's a data company, and it's users' data that is really, and business data that is really the thing that makes companies now valuable, right? We're focusing on making sure that all this data is secured now when it's on the move, when it's being stored, and now actually as it's being processed, right? And so traditional approaches typically have secured the data when it's at rest using encryption to secure the data either through file encryption or through storage encryption, and then providing encryption when that data is in transit from one system to another or from one application to another. Examples there would be something like TLS, and then predominantly, as that data is being processed, that has resided in memory in the clear, and that's been accessible to software that wants to get access to that data. And so with the SGX program, what we've been focusing on is providing protection to data in that final third, so that you can't get to that, or make it very difficult to get to that data, as it's being processed itself. So that's the basic scenario. We're looking after data, and SGX is all about protecting data in use. So let's move on to the next foil, please. So how does this relate to confidential computing? So as you saw yesterday, we created a large organization called the Confidential Computing Consortium, and what that is about is a vision where we're providing protection to compute even in public clouds. And so why has this become relevant? Well, as we've seen over the last few years, big data breaches, lots of data being stored in places that aren't necessarily under the physical control of entities, right? They're very concerned about these valuable assets that they have around. Not only is it business information, it's private information. And so we've been seeking to find a way to, remove large parts of the infrastructure that you have to trust today out of that trust equation, right? Being able to provide confidentiality and integrity to data as it's being processed, but excluding large parts of the infrastructure that might have access to that data. And so generically, the approach to that is to introduce something called a trusted execution environment. And this is a very, very simple idea. The idea of a TEE is really to basically be able to define a bounding box of execution that basically has access to a set of memory or a set of data and a particular set of code running inside it. And once you can do that, then you can start to build out architectures that allow people to say, well, I can trust that application because I know exactly what it is, and I know that it's executing in a more secure environment than what we have today. And so Intel SGX is our approach to achieve that. We've been working on this for quite some time, and as we roll on, it's rolling out through our product set. And so once you have this type of capability, the idea is that with confidential compute, you can now build out brand new usages to do things that we haven't done before, enhance usages that we already have existing today, and really build out a place where you can actually have a lot more trust in public entities and even edge devices and places like that that this compute is going to want to spread to. So that's the vision behind trusted confidential computing and how Intel SGX fits within that. So let's talk a little bit more specifically about the threat model. So as I said, we refer to SGX as a TEE that's a bounding box, and specifically it's an application TEE. So what does this mean? So what it means is that an application vendor can today, if he is trying to keep a secret, if malware escalates to the operating system or the virtual machine manager that's running at on the platform, then it has privilege. It has privilege to see all of memory. And the idea with SGX is that we're going to change the memory access control model such that we make that extremely difficult. We're going to change the access controls. We're going to provide encryption over the actual memory. And so the idea is that your application can keep one or more of these, we call them secure enclaves, running on the platform, but essentially they're a TEE. And so this has a number of benefits, right? One, we're helping protect against software-based attacks on the platform. We're increasing protections for secrets, specifically, initial usage models or about key protection and doing cryptography. But as you'll see with our confidential compute, we have visions beyond that, and we have some further usages I'll talk about later on. And what this really does is allow you to keep the trust boundary very, very small, a minimal trust boundary. And that's good when you're trying to understand what parts of the software ecosystem it is you're really trusting. In addition, we're also going to add protections for physical-based attacks. So at a minimum, we'll be providing, attacks, the sort of the freeze can attacks where cold, compressed air can be poured over the liquid compressed air can be poured over the memory, can be frozen, can be transported to another system. Those sorts of attacks, by encrypting the memory, we provide protection against. And then finally, the main thing is to provide cryptographic proof that actually you're running inside this environment. These whole architectures don't work if you can't prove that your software is actually running in a better place than what it was running previously. And so that's part of one of the big features, and I'll talk a little bit more about that in a second. And so the things that we've done for SGX is really to concentrate on three main things. The first thing is obviously creating this execution isolation boundary for the TEE itself. And that's done through a combination of the way the hardware actually does its memory access controls. So on every memory access, the CPU itself goes off and tries to understand how you're accessing that and will grant or deny your access to memory based on your privilege, your operating mode, what the operating system said you could have access to. We've taken all of that and then enhanced it further to say, okay, you can only access this memory when you're inside the enclave that this page belongs to. We've also added, as memory is evicted out of the caches in the CPU and out into memory, we've added physical memory encryption so that, when the memory sits out in DRAM, that there's protection there. The second big thing is, as I said earlier on, is that we concentrated on this thing called attestation. As I said, there's no point in having these features, these spaces, if you don't know that the software is actually using them. Software can lie, and so what we added was a hardware mechanism that allows the hardware to assert that not only are you running inside an SGX enclave, but actually that the code has an identity, a cryptographic identity, that it loaded into that space, and it can report that too. Obviously, once you've delivered secrets to the platform, you don't want to do this attestation scheme every time you start the application up. And so we have this idea that you can encrypt data on the platform, which is bound to the actual identity of the enclave that you're executing in. And we refer to that process as sealing. So attestation and sealing are a very highly valuable feature that we've added to Intel SGX. And then the third thing that we concentrated on was, well, what if all this goes wrong? We have seen that, we knew that there would be lots of interest from the academic and the security research community in looking at ways of trying to defeat SGX. And so if they have found those ways, what we've been able to do is to issue updates to the platform to provide mitigations for those sorts of attacks. And what we wanted to do was bind the attestation mechanism to say, yes, those new mitigations are in place. And so we refer to this process as TCB recovery. And we see that as a very highly important and highly valuable feature that we can actually say, yes, you have mitigated the latest attack. And so those are three main features that SGX offers, or the challenges that we've had to face as we moved on. And I think I finally want to talk about here is, when we have all these things, what sorts of things can we do with them? Hopefully the next one is the use case foil. So the immediate use case that comes to mind is doing better key protection, whether that be, for processing SSL or doing, little key store type of activities, something similar that looks very similar to hardware security modules. And so those usages we've been looking at for quite some time. But with confidential compute, we've opened up a whole new avenue of different spaces. So the first one is looking at privacy-preserving analytics. So imagine you now have your data in the cloud. It's very, very sensitive information. Good examples of this is genomic workloads. We've seen this in sort of like the cancer research space. Big hospitals have lots of genomic data about individual patients, and they want to be able to share that with you know, cancer researchers and companies in order to do you know, further drug research. But the problem is that they can't just give that information away because it contains very personal related information. And so the idea with privacy-preserving analytics is you can operate on the data in a secure manner without actually revealing the content of the data over which you're doing your computation, and then return that computation to the privacy researcher. Similarly, we have encrypted databases. What we're seeing is that there's been a big fad around tokenization in the data space, so that, you know, simple cryptography can be applied to data, and then matches can be done on encrypted data. This is okay for when you want to do exact matches, but for usages where you've got to actually do range searches and other manipulations of the data, decrypting the data is best. So the idea is you can do this inside a TE itself, inside SGX, decrypt the data, do the operation, return the right result, you know, the right results, and discard the rest, and so that the data in the database is never actually leaked out to the user. And then at the top, and I think Ambuj will talk more about this as we go forward, is the whole idea of actually containerizing full applications such that we can just deploy an application and it can run in a shielded manner. I think we've spoken at great length within Intel and externally about Intel SGX and blockchain. Blockchain is not just a Bitcoin feature, but a way of doing distributed databases. And the idea here is that once you can perform certain operations, whether that's adding something to the chain or doing verification, you can simplify the cost of the blockchain ledger itself. We're also seeing novel usages in the virtualized infrastructure space, certainly for networks. We've been looking at how we provide better protection to the new 5G networks that are coming up and available. And of course, then there's the Internet of Things, and not only having trusted execution environments and SGX in the cloud, but actually all the way out to the endpoint, and then you'll have usages that basically make use of that better together, both on the cloud and the client. So with that, I'll hand on to Ambuj, and he can take it on from here.
Thanks, Simon. So now we have a fundamental understanding of how Intel SGX came into being, why it was conceived, some of the use cases. Let me show you what can be done by applying principles of Intel SGX and confidential compute for your cloud workload. So a little bit of background on Fortanix. We were founded in 2016. We are the first company to use Intel SGX in production environment, just because we thought the incredible power of SGX would allow you to finally be able to run your most sensitive workload in cloud without trusting the CSP, without trusting your infrastructure. So that thrill of solving that problem was so great that I started this company in 2016. We are Series B stage company funded by Intel. We have raised about $31 million. We have dozens of customers, including multiple Fortune 100 companies. multiple patents pending around various aspects of runtime encryption and confidential compute. So that's a little bit background on the company. Next slide, please. So when it comes to cloud security, the first thing we need to understand is it's a shared responsibility, right? When you operate your workload in a public cloud, for example, there is something called security of the cloud, and then there is something called security in the cloud. And the cloud provider provides the security of the cloud, so they make sure that the hardware they are purchasing is good, like BIOS, etc., is maintained. The access to their buildings where those servers are hosted is properly badge controlled and things like that. But all the fun stuff operates at the application and data level. And that's where you as a customer need to own the security of your environment, right? So that includes making sure that operating systems you are using, they are fully patched, right? Your networks are segmented. Identity and access management is huge, right? Doing all kinds of client-side data encryption or server-side data encryption, managing who has access to what database, how your applications are talking, managing sanctity of your keys and certificates. Those are the responsibilities that belong to customer. And the reason for this shared responsibility is manifold. One is that CSP does not really have visibility in your business side, right? So they don't know which application is running where and who are the people who should have access to that application or data from that application. Another is that while customers are moving to public cloud, right, they don't want to get locked into a particular cloud, right? So they want to control their destiny. So that if something comes, either their business changes or they feel need to move from one cloud to another, or they are in a hybrid cloud environment, they go international and now they need to work with a major CSP in that particular country. They can migrate their security policies from one CSP to another, right? If they operate a hybrid environment where they are both on-prem and public cloud, they can apply the same principle. So for all that reasons, security in the cloud firmly belongs to customer, and this is a pretty established principle at this point, endorsed both by analysts, right, such as Gartner and also multiple CSPs. So now we understand what you need to do as a customer. Let's see what we can actually do using Intel SGX and Enclaves. Next slide, please. Yeah, so question is, right, if you operate in cloud, what can you actually do that gives you that security control over your application and data without trusting the infrastructure, right? So as we know, infrastructure is a big security business, right? Tens of billions of dollars spent every year on infrastructure security. But fundamentally, the way infrastructure security works is, assume that you are responsible for securing a city, right? And city has thousands of freeways coming in, and you want to put a toll gate on every single of those highways to screen all the incoming people, all the incoming vehicle, all the cars, trucks, etc., etc. And as you can see, this is a humongous operational nightmare, right? And just when you thought that you were able to screen maybe 99% of the incoming traffic, now you suddenly discover that there are like 5 more highways being built. And as you are in planning phase for taking care of those highways, now you see that underground tunnels popping in, right? And as you are trying to figure out what to do there, now there are drones coming in. So the madness to secure your city by relying on this kind of distributed perimeter control is very, very hard. It's certainly effective in some cases, but it's not going to really take care of the problem, right? So what you can do instead of doing that is you can take your application or data that you really care about and decouple security of that application and data from the underlying infrastructure. So rather than trying to secure your infrastructure, assume that even if the infrastructure is compromised, right, what can I do that can still keep my data and applications secure? Because if you crack that puzzle, then you are not really dependent on the infrastructure security, right? Then you can take your most sensitive workload, most sensitive data, can put on any cloud you want without worrying about the infrastructure security. You will still apply all the best practices of infrastructure security, right? But then you are firmly in control of your all the security and privacy policies. And that's where enclaves come in, right? So enclaves give you a predefined, very flexible region in CPU where you can rely on security endorsement from the hardware to keep your application and data secure. It's not dependent on the infrastructure, right? So even if people get inside your network, right, inside your VPC, they can try some privilege escalation vulnerabilities, etc. Your enclaves may still be able to protect you from some of these attacks, right? And by doing that, now you also get portability, right? Since everything in cloud finally runs on some kind of hardware, right? And that hardware includes CPUs. If you are relying the underlying security primitives from CPUs, you know that they will be available on any cloud you go, right? So as different cloud providers, they have different access controls, different methods. If the underlying hardware is the same, you can just exploit those security features offered by CPU for your security policies. And that's where Intel SGX come, right? Intel Software Guard Extension. It provides those enclaves using Intel CPUs. So as a company, Fortanix, right, we rely on that. And we provide you all the software and tools, and we take your applications run inside enclaves. And by doing that, we provide you that migration path, right, from one cloud to another. We decouple your security from the underlying infrastructure. And by doing that, we remove the security barrier to cloud, right? So if you are a CIO or a CISO, right, and you are evaluating whether you should migrate your application workload to public cloud, there might be 100 reasons, 100 things to worry about. Our goal is that security and privacy concerns shouldn't be one of those. Next slide, please. Yeah, so Intel SGX ecosystem is fairly robust at this point, right? So as we saw yesterday, Linux Foundation built the consortium, but there are multiple players already. I would like to highlight some of these, right? So in cloud providers, for example, Fortanix has deep relationship with IBM Cloud, where they offer a service called Data Shield. And idea is that you can take your most sensitive containers to IBM Cloud, and without you worrying about anything about, you know, like Intel SGX, understanding its ISA, etc., or recompiling, rewriting your application, that container will just run inside enclaves using the software we have built. So that software we call Enclave OS. And what Enclave OS does is it takes your application and just run inside enclave by kind of virtualizing the enclave provided by Intel SGX. You don't have to rewrite your code. You don't have to recompile your code. But that's not all, right? Once your code is running inside enclaves, now you need to manage the life cycle of it, right? So that's where we have built our Enclave Manager. So Enclave Manager gives you that complete enterprise control over various enclaves that might be sprinkled across different clouds, your own data centers, your developers trying to do something to one cloud provider, to another cloud provider across the globe. So Enclave Manager, your single pane of glass, visibility into all your enclaves. And using our own platform, we built something called SDKMS, so Self-Defending Key Management Service. It is cloud era, cloud native, you know, like distributed next generation HSM. So if you are trying to secure your databases. You want to encrypt your database. You want to get some kind of tokenization or field level encryption. You want to secure your certificates, etc. STKMS offers that capabilities. We also have something called EDP, Enclave Development Platform, right? So Enclave OS product is built for bringing your existing applications into Enclave, right? But if you started from a scratch and you are building some application that is really security sensitive, and you really wanted to make sure that this is the most secure application, what would you do? So EDP is our answer to that. So we say that, look, like if your application is that sensitive, you should use Rust. So Rust is a new system programming language like C, C++. So it's very powerful, very performant, but it is a modern safety first language, right? So it's thread safe, memory safe, type safe, etc. So it makes it very hard for developers to make some of the mistakes that are seen in other languages. So Rust provides you protection from inside. And then if you use our EDP, it's a simple command line compile time target for SGX. And when you compile your Rust code, now you get an enclave, and your code now runs inside enclave. So EDP provides the protection from outside using SGX. We are also partners with Equinix, right? So Equinix is one of the world's largest data center provider. They take our STKMS product, offer it as a SaaS under Equinix Smart Key brand. But as I said, there are other companies, other players in this field, and SGX ecosystem is actually fairly robust with both smaller companies, dedicated companies like Fortanix, to some of the world's largest companies. Next slide, please. Yeah, so how does runtime encryption works? So RTE, or runtime encryption platform, is software that we write. It works at the application level, right? So one of the fundamental strengths of software guard extension is that it's an application level code, right? So for those of you who are familiar with TPM, the TPMs had multiple shortcomings, but one of the challenges was that if you are a pure application developer operating in cloud, it was very hard to get all the benefits of TPM. Now, Software Guard Extension SGX was created for this cloud era, right? So you can fully leverage SGX without worrying about, without having control over hypervisor, without having control over operating system, right? So similarly, the software we provide, RTE, it's application level logic. So what that means is, if you have native applications running, right, we can support that. If you have containers, then we can support that. If you are inside VM, that also works, right? It doesn't really matter because it's all ring-free code. So the target use case here is that you bring your container-based applications, right? We take your container, we create another container, right? There is a manifest file that tells us where is your binary or a.out, right? And now we simply insert our RTE in the runtime, right? So instead of like running a.out, for example, now it will run Fortanix, and a.out would be a command line argument to that. So your application runs as before, but now it's running inside Enclave. And then you can take that modified container and run on any server that has SGX, right? And we work with Kubernetes, etc. So you can use your container orchestration framework that you have, nothing changes for you, but suddenly you have all the protection offered by Intel SGX. And again, this is built for cloud, right? So, and the biggest marquee use case for us is IBM Data Shield, right? So if you are not using RT, for example, you would upload your containers to IBM Data Shield, IBM Container Service, and it will run your container. If you use our runtime encryption, you do exactly the same thing. You upload your container, your behavior doesn't have to change. You simply check a box, and now it's running protected. And that's really our vision and promise, that once Intel SGX machines are everywhere, all your security sensitive workload will run inside Enclave using something like this. Next slide, please. Yeah, so the way RT again works is it works with your Docker Kubernetes based standard tools. If you are using some kind of CI/CD, it just works like that, and you don't have to basically do anything at your developer level, right? You just bring your fully functional container, you get another container out, and that container out goes to your CI/CD. It gets deployed on a machine that has SGX, and it just runs. Or you can also use our EDP, Enclave Development Platform, right? In case of EDP, what you are doing is basically you are writing a new application from scratch. You chose Rust because either you needed performance or you needed security. And in that case, basically, it's just simple. We are already integrated with Rust compiler, so you don't have to download any external SDK or anything like that. It's a simple compile and change, and voila, now you have a SGX Enclave. Next slide, please. Yeah, so this is one-click cross-cloud Enclave deployment and monitoring, right? So what you are seeing here is a little bit detail on how it works in practice, right? So towards the top, there is Enclave Manager, and Enclave Manager gives you visibility to basically all your enclaves, right? And when you are deploying enclaves, you get lots of controls, right? So for example, now there are various kind of data sovereignty laws, right? Whether it's California CCPA or GDPR in Europe, right? Or India has its own law, China has its own laws, Brazil also has something similar, Russia is also bringing something same. And all of these countries essentially tell you that if you have some kind of sensitive data and you want to do some kind of processing, these are some of the restrictions you have to follow, right? And restrictions could be that you cannot do X, or it could also be that you can only process this data in my country, right? Or in this region. And there are multiple ways of handling that, but the way SGX comes in, since SGX is based on CPU, essentially when your Intel servers are deployed in your data centers, we allow you to assign some attributes, right? So you can say that, oh, this server is based in Germany and it's used for healthcare data, right? This server is based in Germany and it's used for financial data, right? This hardware is based in US and it's used for healthcare data, right? And now, once your containers come in, right, you can put policies. You can say that, okay, this container can only run in Germany, and then you have some data, healthcare data, and you can put policies on that data and say that, look, like the keys that have encrypted this healthcare data would only run on machines that have been tagged to process healthcare data. And by combining these kinds of attributes, you can ensure that you are processing data in right way, in right location. And you can also control, like, these are your applications and they are also running on the machines where they are authorized to run. And what's the best about all this, that these kind of attributes and this kind of enforcement, they are not done at software level. So it's a software flexibility. Applying attributes is as simple as going to Enclave Manager and typing, a couple of texts. But underneath that text box, what we are doing is we are issuing a X509 certificate, right? With that being one of the attributes, your text being one of the attributes of the cert, and that cert is issued to a particular system with Intel SGX, right? And if you try to take the same cert to some other machine, it will not work because the other machine will not have the private key corresponding to the cert. So it's all cryptographic certainty and enforcement, right? So it's not a software level simple ACL that some other software will be able to bypass. So it's very, very powerful, very, very flexible, and cryptographic in nature. So it's really robust. And we do all that using our enclave manager, right? And of course, if your systems are going down or you need to transition from one SGX machine to another, one of the very frequent comments we get from our customers is that, hey, if I have a database, I encrypt that database and I'm running on a particular SGX server, and if that server dies, what happens, right? And which is a valid concern if you were relying on some keys that were just tied with one CPU, right? And that CPU is no longer accessible. What do you do, right? So what we do is basically we can create a group, right? So you can have multiple servers, and each server is individually recognized, right? They each have their own processor specific keys, but using those keys, you can build a tree-like structure, and there is some sort of virtualization of keys, and that common group key can then be used to actually encrypt and access your database, right? So in that case, if one machine dies, you can go to the next machine, you can enroll a new machine. So all this node provisioning, node enrollment, whitelisting, certificate management, monitoring, etc., is a very complex orchestration, and that's what our enclave manager does, right? So think of it as your single pane of glass, enterprise-grade management framework for all your enclaves around the globe. Next slide, please. So when we talk about use cases, this is one use case that we have seen resonate with multiple of our customers, and we have gotten multiple customers ask about some variant of this use case. So this is such a powerful concept, and it demonstrates what can be done with enclaves that was simply not feasible earlier, that we wanted to highlight in this webinar, right? So here there are two parties. Party one, for lack of better words, call it a telco, and party two is a bank. And assume that party one has some customers' data, right? It's a simple list of customers who are basically name and emails of people who are customers of the telco. And similarly for the bank, right? Bank has a list of their own customers. And all they want to do is basically find names and emails of common customers, right? People who are both the telco customer and bank customer, so that they can run some, like email campaign, for example, right? Now, how do you do that? So simplest one is that telco sends its customer list to bank, right? And bank can figure out, okay, these are the lines that are matching, and they can print it out. But the problem with that is if bank has access to all the customer lists of the telco, right? Then telco is not happy, because bank can also go after other people who are in that list who are not the bank's customer, right? So bank has access to more data. And similarly, vice versa, right? Bank will not want to share its customer list with the telco, right? So of course, they can rely on contracts that they can say that, look, like, I'm going to send you data, but you can only use for this particular purpose, nothing else. But as we know, legal frameworks have their own challenges, right? Or they can rely on a third party, right? So they can go to a notary and say that, okay, notary, you can, we'll send you to databases, and you will do this, and you will give the common name. But the challenge then is finding this notary who is trusted by this large bank and this large telco, right? So you simply defer the problem to somebody else. So those were traditional frameworks, and realistically, we have seen that people have not been able to fully share their data according to their own privacy controls and their security controls, because traditional framework simply doesn't work. So what we do here is we use enclaves to solve that problem. And the concept is very, very simple, right? So you take telco data, you encrypt it, you take the bank data, you encrypt it, you put the two keys for those two databases in some kind of HSM, right? Here it's shown STKMS. And then you write a simple Python application, right? And Python application is just reading line by line of one database, and it's reading line by line of the second database, and it's finding name of the common customers, and it will print out their names and emails, right? And then that Python application is now running as an enclave on a system, right? Now, first thing that happens is when this application start to run, the telco gets notified, the bank gets notified, and the security architects there, they can look at, oh, this is the hash of the particular application that's running. And I can verify that that hash means that this application, all it's trying to do is finding the name of the common customers and nothing else. And since I trust this application, I'm going to say yes on this Enclave Manager screen. And when you do that, then Enclave Manager essentially issues a cert to that application, and then that application authenticates itself to SDKMS, and it gets keys, both the keys, right? So when the telco says yes on Enclave Manager, it will get the telco key. When the bank says yes on Enclave Manager, then the Python application will get bank keys, right? And now the Python application has both the keys. It can simply decrypt the two databases and run. Now, from the Python's application perspective, it's really simple. Nothing really fancy happened, right? For security architect's perspective, it's really crystal clear that, hey, I have a cryptographic identity of the application. I issued a key there, and that allowed this processing to happen. And what is really beautiful here is that all that processing is happening inside Intel SGX, right? So keys are never exposed outside SGX. They are always kept within the boundary of enclave, right? When you issue a cert, that cert is basically tied to that application. All the TLS traffic always terminates inside SGX enclave. So really powerful use case. Next slide, please. So these are some of the use cases, right? So AI, ML, we saw this processing, Python application, telco bank, that's one use case. Blockchain, Simon talked about that. Secure containers, of course, as you move away from VM, and VMs have lots of problems, right? Primarily performance, orchestration overhead, and there are lots of companies now exploring containers. And the biggest thing, one of the biggest things in containers that are keeping containers from getting fully deployed at production scale, etc., is security. Because containers, if there are multiple containers running on the same machine, one container gets compromised, you can compromise other containers. And by using something like Fortanix Runtime Encryption, containers are now running in separate enclaves. So you get much better isolation than traditional VMs. You can run MySQL, Nginx, Vault, Barbican, OpenDJ, etc. Today with Fortanix. Network security, of course, is a big one. Next slide, please. Yeah, so this is last prepared slide, right? So whenever we talk about Intel SGX, invariably people ask about security, etc., right? Side channel vulnerability is real, right? It impacts you. It might impact you whether you use SGX or whether you don't use SGX. There are some defense that can be built at the application level, that can be built at platform level. There are some defense that can only be built at the application level, right? Some of the defense we already put inside Fortanix framework, and it's quite complicated. So what we did was we wrote a white paper that describes side channel from first principle, right? So we go about taking a very, very simple, easy to understand use case and say, okay, this is how the side channel vulnerability is. What is side channel vulnerability, right? This is how, if you're trying to open a lock, your keys might leak, right? And then we build upon that to give you what a Spectre, Meltdown, etc. are. So I will highly encourage you to look at that PDF. And then when you build an application, right, such as SDKMS, and security is your first goal, you need to do a whole bunch of things, right? You need to really understand what the platform provides, what you need to do at application level. Some of the things that we do inside SDKMS, of course, it's secured by some of our IP rights and patents and trade secrets, etc. But some of the things we are comfortable talking about here is that, hey, we use AES NI instructions. They only run in hardware, right? We build some of the side channel resistance, right? Very simple is that if you are trying to match a password, right, two passwords and see whether it's a good password or not, if you are not careful, people can do simple side channel analysis and can figure out what the good password is. And there are standard practices for that. And again, some of this you'll see in our white paper. And again, there are always best practices such as keep your BIOS, OS updated, etc. And then we have our STKMS runs in an appliance that is FIPS certified. So those are some of the best practices we do. And again, we highlighted that because if you are an application developer, right, or you want to use Fortanix to run your application inside Enclaves, you have to be really careful about what are your security properties that you want, and what can Fortanix do, what can Enclaves do, what can Intel SGX do, and what you need to do at application level. So I think that concludes our prepared content, and now we are open to questions and answers. So first question is, very interesting use cases. Can you guys give some background about performance when computation is done in T compared to usual computation? So I'll share my thoughts, right? And then Simon, you can also chime in. So what we have seen is it varies based on your workload, right? And if you are building something that is very, very memory intensive, right? And then you might have some more slowdown. But in our case, where you have, let's say like maybe 1 million customer record, right, with the bank, and 1 million customer record of at the telco, and you wanted to find common customers, there will not be much observable. We have not seen any observable, like performance penalty, because the time it takes for your applications to load in memory and start to execute, SGX component is such a small and so fast that it doesn't really matter. And your TLS, establishment, etc., back and forth, that will, for example, dominate, right? So it depends on the use case. We have published some of performance benchmarks, right? So you can go to fortanix.com/Intel SGX, and you will see some more data there. Simon, you want to chime in?
So I think there's a couple of things we can add here, right? So there are, when you add security, right, there's always going to be more checks to do. And so there are different latencies for different reasons that get added. And obviously, our job at Intel is to, obviously, over time, ensure that the performance improves. And, we've got a very good track record of, taking particular performance pain points and making them better over time. So for instance, if you look at the VT set, instruction set, started off as being quite slow, and then as hardware improved, you got performance benefits, and it didn't actually cost you anything from a software perspective. So things that we look at, right, are the transition latencies for going inside and outside an enclave. Obviously, the memory encryption obviously adds a latency, and these are things that we can improve upon, looking to get those reductions out. And I think something that Ambush said about, depends on the workload. Let me give you for instance. We did an example of, looking at just calling inside an enclave, doing a very simple operation and coming outside an enclave. And we looked at, RSA signs. So a 2048K RSA sign, the cost of transitioning inside the enclave was amortized enough that actually the performance adder for that operation was only about 1%, which I think is very reasonable. Now, obviously, if you have an operation that's much shorter, the same transition time is amortized over a small amount, and therefore that the workload seemingly slows down a little bit more. So, it's really about, you know, how long do you spend inside the enclave to amortize those costs, and how much of your working set are you fitting within the cache? And so those things are always sensitive. You can performance tune, and obviously, you know, our job at Intel is to, you know, over time alleviate those, but not change the software infrastructure required to support them.
Yeah, I mean, one thing I can say is like Intel over last, you know, 50 years, like Moore's law, every year is 10, 20, 40, 50% faster. So if, yeah, I mean, and that trend continues, right? And what Simon says is also very apt, right? That by using SGX, you can build a system that is more scalable. So for example, STKMS, right, horizontally scales. So if you are looking for a you know, high performance system, we got that. Now some other quick question and answers, right? So what encryption algorithm is used in runtime encryption, right? So we use a standard encryption schemes. We are not, you know, here in business of developing new encryptions, right? So it's a standard AES, ECC, RSA, etc. Another quick question is, how do you stack against database TD like Oracle, etc.? So Oracle TD, I mean, one of primary use cases we see for STKMS is enterprises buying our solution to secure the keys for your Oracle database. So that's there. Then there is a question about multi-party analytics, very interesting use case. How do you verify enclave attestation? Do they need Intel SGX SDK, or is it a simple, easy call IES API? Also, it's supremely easy. You don't even have to know what Intel IES is. It is simply basically verifying your certificate validity, right? So Fortanix takes care of basically talking to Intel IES service, then issuing a cert and all that. We give you a RESTful API, you just call that, and you know that now different applications are running inside Enclave. I think those are the questions we have. Thanks again for your time, everyone. This is first one we did on Intel SGX with Simon and myself, right? And we look forward to basically doing more in the future. Thanks again.